Let's talk about virtual memory. In general, we have two memory addressing systems. One is physical addressing systems, and the other is virtual addressing systems. The physical addressing system is straightforward. The CPU issues the physical address, and memory is accessed with that physical address without any change. Such physical addressing is still widely used in simple and embedded systems such as elevators, digital picture frames, refrigerator, microwave, etc. Such simple systems do not benefit from virtual addressing as they run always the same code or program. Now, the virtual addressing system is more complicated. The memory address CPU issue is a virtual address, and it must be translated to physical address before accessing the memory. In virtual addressing system, the processor has a hardware block called MMU, Memory Mapping Unit, that is responsible for translating virtual address to physical address. In this simple diagram, CPU issues a virtual address of 4100 and MMU translates it to a physical address of 4. And then the memory is accessed using a physical memory address 4. All modern general-purpose computer systems use virtual memory addressing, and it is one of the great ideas in computer science. Let's talk about why virtual addressing is good. First, it makes the programming so much easier. Without virtual memory, programmer or compiler have to manage the memory address manually, and efficient memory management is a very challenging task. Second, it makes so easy to use DRAM as a cache for large virtual address space, and it's done by hardware and operating system automatically. Third, it simplifies memory management significantly among multiple programs running concurrently. Each process gets a uniform linear memory address space, and physical memory management is taken care of by the hardware automatically. Fourth, the virtual memory system makes the memory protection so much easier by being able to isolate memory address space easily. There's no way one process interferes with another's memory, and there's no way for user program to access privileged kernel information. Programs stored on disk are compiled with the virtual memory by compiler, and their virtual addresses are cached into physical DRAM. A cache block or cache line in this situation is called pages. The typical size of a page is 4 kilobytes, while typical cache line size is 64 bytes. Unlike in cache memory, the caching between DRAM and disk is handled by operating system. In the diagram, we see that virtual page number 1 is cached into physical page number 1, and other two pages are also cached. Let's talk about the page movement between main memory and disk. Unlike cache memory, the moving data between main memory and disk is very expensive because disk is very slow. Because each transaction takes a long time, we move larger chunk at a time. That's why page is a lot bigger than cache line. Also, we use a fully associative configuration to avoid or minimize any conflicts. A virtual page can go anywhere in memory, and it also uses highly sophisticated, expensive replacement algorithms implemented in OS, operating system, and use write-back policy rather than write-through policy. Let's talk about address translation. A data structure called page table plays a key role in address translation. The page table is simply an array of page numbers. The virtual page number becomes indexed to page table, and each content is a physical page number. In the diagram, the virtual page number 1 is mapped to the physical page number 0, and virtual page number 2 is mapped to physical page number 1. The virtual page number 4 is mapped to physical page number 3, and virtual page 7 is mapped to physical page number 2. Each process has its own page table, and page tables are stored in DRAM.